everyone, I'm Boots. And later at 8 o'clock, and I have dinner with Dora. And I think I have time to play some games. Yes.
Boots, where are you? Look at this clock on the microwave. It's 8:30.
Huh?
We have dinner at 8 o'clock.
What?
Do you remember it?
Bro, it's 7 o'clock and
Impossible. What are you doing now?
I'm pretty.
Impossible. What's this? Such a boring game.
What? What are you saying?
What's
This is
this
the-
game?
This is my favorite game, Arena of Valor.
What? Arena of Valor? I rather listen to Arena of Valor than this Arena
Wow.
of Valor.
You.
How dare you? How dare you?
So noisy.
Shut up,
Everybody
you.
shut up. Shut up.
Shut
I will
up, you.
time stop you.
Shut up.
Microwave? The microwave says 8:30, but it is actually only 7 o'clock. Wow, so weird. Let me tell you why. 来，同学上课喽。我的小老师呢？这个投影幕怎么没有拉下来？ Okay, so why was Dora's clock faster than Boots's? Well, we're going to get into that in today's topic, power systems and clocks. So typically, a digital clock relies on zero crossings of the AC power grid to calculate time. So every time the voltage crosses a specific threshold, the clock will know that it's been a certain amount of time. But if the input isn't a perfect sine wave, as you can see here, it's got these tiny little bumps, the clock will think that it's faster than it really is because the voltage crosses the threshold multiple times. And that is a problem. So the voltage wave might be bumpy because of harmonics. So, which we will talk about in detail later. And that causes multiple zero crossings, which results in the clock's time to be faster. And we fix that by using the Fourier transform. The Fourier transform is a mathematical tool that converts the time domain signals, like from a clock or a clock, into frequency domain, allowing us to analyze the strength of various frequency components in a signal. So in this context, the Fourier transform can be used to examine the harmonic components in the voltage waveform, and so that we can understand how they affect the number of zero crossings. So why aren't power waveforms perfect? So here's the thing. The electricity we use at home isn't always a perfect sine wave like we see in textbooks because, well, this is real life. And in real life, the nice, smooth sine waves get messed up, and that is because of harmonics. Harmonics are like an extra noise in the electrical signal. They sneak in when we plug into certain kinds of devices, especially non-linear waves. So what are those? Basically, any device that doesn't draw current in a smooth, consistent way, like think of things of your laptop charger or LED lights, phone chargers, air conditioners, And these devices are super common now, but they kind of pollute the electricity, making it harder for other devices to work properly. And sometimes it can, cause damage over time. So even though we're using more energy efficient tech, we're also creating more problems in our power systems. These nonlinear devices, we just talked about, they cause harmonics. And the voltage in our homes follow a simple sine wave, like this one. That means it oscillates at 60 times every second. which matches our power grid's 60 Hz frequency. And that gives us 120 zero crossings per second. 60 going up and 60 going down. But when harmonics kick in, things change. For example, this one. This extra sine wave, this one right here, this is the 5th harmonic. And at which you can see it is at 300 Hz. That extra sine wave will distort the waveform and cause the waveform to have sharper peaks and dips, and you can run into real world problems like devices misreading zero crossings, like Dora's clock, or potential quality issues. So even though we don't see it, the tiny distortion can mess up with a lot of stuff in the background. So here's a visual that shows exactly what we've been talking about. The blue one is the original sine wave, and the black one is the sine wave, the function with a harmonic inside. On the left, we can see the ideal waveform. It is clean, right, the blue one. That's what we wish our power grid gave us. But if we look at the black one, it is messy, and we don't want that. These sharp changes can cause problems for devices that rely on timing or expect clean power, like clocks, sensors, or audio equipment. It's kind of like trying to listen to music with background noise. It's still there, but it doesn't sound as good. So now we know that there are harmonics in the original frequency, the wave. But how do we find these harmonics? Well, if you remember the formula for the Fourier transform, it kind of looks like this one. And each term in the sigma function is actually a harmonic. So this is like n is equal to 1, n is equal to 2. And if you use the Fourier transform, you can find every single harmonic. And then if, say, you don't want the third harmonic, you use some kind of contraption to filter it out. The first harmonic is also called the fundamental frequency. So how do we solve the problems? There are a couple ways of dealing with harmonics. The first method is you can use hardware to filter out harmonics. We can use analog components to physically block the unwanted frequencies. For example, we can use a low-pass filter. It only lets low frequencies through, like 60 Hz, and it blocks the higher frequencies. A high-pass filter does the opposite. Bandstop filters, or notch filters, remove a specific frequency, like 300 Hz. And finally, EMI filters clean up electromagnetic interference before it reaches the device. A few places these are used in are air conditioners, refrigerators. They filter out the compressor startup surges and harmonics, or TVs and audio systems, which help reduce noise. Power supplies also use inductors and capacitors to filter out unwanted harmonics. Okay, the second method is using software filtering. So in digital systems, signals can be processed in the frequency domain to identify and remove unwanted components using software techniques. Here's the process. First, you use the Fourier transform to convert the signal into frequency domain. And you identify the unwanted components, say 180 Hz or 300 Hz, and you apply a digital filter. It could be one of the 4 we talked about before. And then lastly, you use the inverse Fourier transform to convert the signal back into the time domain. A few places where software filtering is used in is smart meters for real-time filtering, solar inverters to clean up AC output, and power analyzers to detect harmonic distortion. Yeah, and that is why Dora's clock is faster than Boots. Thank you. 肖老师来出题目吧。今天的课就到这里。
997，998，999。疗愈。哦。但是我现在问题是，60，你拿到网，然后我要回去侦测说，多人不知道。